Maybe first, before we start, I just have like 3 questions. Has anyone familiarity with the summarize experiment class? Okay. Yeah. Okay. And who has familiarity with statistical concepts? So experimental design, p-test, linear regression. Okay, mostly that's cool. And familiarity with mass spectrometry-based proteomics experiments. Okay. Is there anyone that didn't raise his hand twice? Okay, that's perfect. Well, because otherwise, if you don't have, what I would suggest is don't try to fiddle with the code, but like as you can just follow along with the code, play with it if you want. But there will be some concepts that on which I will, first, if you want to go into the workshop, the very first thing you have to go is to go to this link. So workshop.bioconductor.org. You'll see there is a window that will open asking you to log in. If you don't have done so, you also have to register. It takes 2 seconds. What? Du shame. Is everybody able to get on this page? Who can't get on this page right now? Okay, I'll wait a little bit. All right, you have internet problems. Okay. Well, I'll just carry on. Sorry. Well, for those that were able, yeah, thanks. For those that are able to attend this page, well, just click here on the sidebar in workshops. You go msqrob2 workshop. Once you click on that, you'll see the change. Just have to click on run tool. And once you did that, you'll see it will change to these 2 boxes. Then you have this line. It will ask you to wait a bit for the interactive tool to open. And after a few seconds, you will have this link open. And you can click on it, and then you get into, then you're asked to do that. Okay. For those that have connection, are you already in RStudio? Oh, do you see the RStudio opening? Yeah. Oh, who doesn't see the RStudio opening? Okay. If this link doesn't work, I mean, if you have, doesn't seem to update, what you can also try is normally this little tile that appeared. You can also go there and then click on the link that's provided, and it will also open there also. Yeah. Ria, did you manage to? Yeah. Okay. Thanks. Sorry. Okay. Who still needs to be set up?
Yes, just carry on.
Yeah. Okay. So for those that are able to go to studio, at the end of the presentation, I will provide also links. If you're interested, you can just like run the workshop at home at your pace with internet. So, but yeah, so normally if your RStudio has got initiated, there will be this page open, the vignette, which we will go through today. And I suggest to start with a since most of you are used to mass spectrometry-based proteomics is just going through a brief recap of how the experiment. So the idea is we want to understand how a condition, how a perturbation, how a treatment would influence the proteome. That's the idea of proteomics experiment. So what you do first, you collect some samples, and then you digest them. You digest them, so that means you extract the proteins and cut them into little peptides. In this case today, we'll be focusing on special workflow, a labeling workflow, meaning that we can measure multiple samples at once. I specifically choose to choose that workflow because it's a complex design, so we'll see it will bring some peculiarities that we'll need to take into account during the model. But so keep in mind the peptides are then labeled, very specific labels, and then once each peptide from one sample is labeled, samples from different samples with different labels are then pulled together and sent into the liquid chromatography and morphology. So the liquid chromatography idea is to have some sort of, I mean, the pool of peptides is gigantic, so you want to kind of reduce the complexity by separating peptides based on some typically on the hydrophobicity. Once they elute out of the LC, they are ionized. So again, what we're measuring is not in proteomics, it's not proteins, but it's peptide ions. Coming out of the once ionized, they can be sent to the mass spectrometry. And then we will scan the first time what are the different masses of charge of what is coming out of the chromatograph. So we have different peaks, and basically one peak is typically one peptide ion. This doesn't tell you, okay, you have a peak, but doesn't tell you, okay, what is that peak? So what we do is a second round chromatography. So each peak is selected, and each peptide ion is selected, fragmented, broken into pieces, and then we measure what are the scatter of. If we look at this range, the pattern of how the precursors profile of these precursors will give you an idea of what's the identity. And then we can do from the spectrum, we can assign a peptide identity. We have then a peptide spectrum match. That's awesome. And if you focus in another region, here, like in the low mass region, well, actually, what are those peaks? Those are the fragments generated by the labels that we put in the beginning. But they come out at the second round mass. And the intensity of those peaks will provide you with quantitative information of how much peptide was there in my initial sample. Right, close. Okay, so that's mass spec in a nutshell. Now we don't know this, so this is all the introduction. Today we will learn how to best analyze this type of data. So assuming that the experiment has been run, people have acquired this mass spectrometry data, and then they put this data into a search engine. So we have the spectra that are identified, the PSM matches with the quantification information. The first thing we will do, obviously, is to load our packages. So the main one today, well, our focus today is msqrob2, but there are also other packages that we need. Yeah, typically these are like data manipulation and visualization tools. Probably most of you are familiar with them. And then we'll get, we'll initiate the parallelization. So msqrob kind of splits the computation on different nodes if you want. But here in this case, to make it simple, I mean, I don't know what your setup is. So to keep it simple, we will just not parallelize. So we use the parallel. In this case, we do serial parallel, just meaning we don't do parallelization. There are other options. I suggest you to check out the package documentation is very well written. So how can you set up a parallel environment? And then, yeah, so now next, let's go to the data itself. And before we get the data, let me also show you what is the experiment that was mentioned. So in this case, I will demonstrate msqrob on a data set published by Prudel et al. And they were interested in understanding what's the impact of diet on the protein in mice. And so what is the impact between a low-fat diet and a high-fat diet? And also, what is the impact if I have a short diet of 8 weeks or a diet of 18 weeks? So to test this, they assigned 20 mice into 4 categories, either low-fat, high-fat, and within each category, short duration or long duration. The peptides were extracted, And once they were extracted, we have the digested peptides, they are labeled, and they are mixed, they are put, as I said in the beginning, they are put together in what we call a label mixture. As you can see here, the mixture contains 10 labels, and we have 20 mice. Well, you cannot put all the mixtures together. There are also like additional samples that we will that the authors included that we will not use today. So basically, you don't have enough room, you don't have enough labels. So what is happening? Well, you do just 3 times this experiment. You have 3 mixtures with containing a different mass. And then they did something else. It's like every mixture that you did, they didn't send it directly to the mass spec. What they did some fractionation. So this means they took part of the liquid chromatography and they acquired it in a separate run. So every mixture has been acquired in 9 fractions, 9 different runs. This is important. Again, I'll come back when modeling because this brings some correlation. We expect the intensities coming from the same fraction to be more similar than intensities coming from different. I'll come back to that later. So the data has been deposited on what was it? Massive. It's on Massive, but we also timestamped it on Zenodo, so making sure that this workshop will be eternally reproducible. And to retrieve the yeah, let's hope so. And to retrieve the data, I here use BioC file cache. This is very interesting because well, we'll see if I run this. BioC file cache will allow you to retrieve resources. So for instance, here I'm retrieving PSM data. It will retrieve your resources, but will store it on your local disk so that you only have to retrieve it once. So here you can see it takes some time to run. It's downloading the data from Zenodo. And I'll show afterwards, if I run it the second time, it will be blazing fast because it knows I already downloaded it. I'll fetch it from my local. I think this is a very powerful tool, and I would really advise you to use that, especially if you have archived links. Well, this allows you for reproducibility. So it's still downloading, but in the meantime, I can tell you what are the 2. So we will be downloading 2 files. What I call the PSM table and the annotation table. The PSM table is the data that comes out of a search engine, which basically took all the spectra and tried to add these labels. You remember I said we have these MS2 profiles and we try to assign it a peptide information. Which peptide did it belong to? This is what has been performed by a search engine. In this case, the search engine is called Skyline, but there are many other search engines, and if you use the proteomics, you can use any search engine you like. Yeah, to be honest, I don't have a favorite search engine. One I notice works less well is msqrod2. I mean, I did a few comparisons, and yeah, msqrod2 usually, and other people made some comparisons. msqrod2 tend to be less performant. But yeah, I mean, yeah, Skyline is interesting, but if I'm not wrong, it's paying. You have to pay for it. You have Sage, which is an open source alternative, which seems to work pretty well as well. So yeah, I don't have a preference, but anyway, I think it's not. I don't feel competent enough to say I'll provide better. This is the better search engine. I think other people do better work on it. What I want to do is provide infrastructure that people can read in all these different formats and be able to compare them if they want. That's possible. I won't cover this today, but this is possible with the infrastructure. In the meanwhile, yeah, it has been downloaded. Yeah. If I do this, you can see. So it's I just mentioned what was the PSM data. The annotation data is very important as well. This provides you information about the different samples. Let's dig into this in more details. Let's be more concrete. So I have this PSM file. I read it into R. and then I visualize it. And this is basically what it provides. It provides a lot of information. Wait, let me. Yep. It provides here a lot of different pieces of information. Yeah, but the one that's that interests me. So basically, this information have been generated by the search engine. Something that is interesting, for instance, here you can see. So again, every line corresponds to a PSM. Something that is interesting here, we have the peptide identity that has been labeled to the spectra. Another piece of, oh, sorry. So yeah, this is again different pieces of information. Here you have the protein accession column, which is also interesting, saying, okay, the peptide that I identified, to which protein does it belong? And sometimes you can see it was not able to unambiguously map a peptide to a protein. Sometimes one peptide can have multiple proteins. You can see it there. Yeah, then you have all sorts of scores. I mean, I won't go into these details right now, but I will be focusing on these columns here. You can see you have abundance, and then these different tags. Actually, these are the tags of the labels that were used. Well, one label is called 126, and you have 127N. So this is the quantitative information that came out of the software. So telling you remember those little peaks that were higher or lower depending on the label. This is what has been quantified, and you will see later. We will use this information for the data analysis. This is, let's say, the core information that's interesting for us. So in the PSM data, we have PSM annotations and we have quantitative data. Then we also load the sample annotation table. And here what we have is different information for a sample. Every line here corresponds to one sample. And the sample has been annotated with different information. For instance, very important, which label, well, it's called channel, but which label has been used to mark that given sample. What is its condition? So here, for instance, it's long. You remember we have these different mice with different diets. It has been treated with a long diet, LF, or with low fat. So low fat diet during a long duration. We also have the label of the run, in which run has it been acquired. You remember we have different mice. Each mouse has a tag as well, which we store it in the biological replicate, the bioreplicates information. It says, you remember there were those pools of different samples. Well, this pool has been, those pools we call them mixtures. They have been assigned also a label, and then every mixture has been fractionated into 9 fractions. We also have the fraction information. Obviously, these information are it's very important to be able to link the quantitative data with these annotations, because otherwise we cannot do modeling. So what I do here, it's a little bit more, well, I mean, here I extract, so we have the condition, I extract the duration information, I extract the diet information. Basically we see, so now we have mice, so the duration is either long or short. The diet is either low fat or high fat, or other others, but I'll mention it afterwards. We'll ignore the other conditions. And then I rename channel. I find it confusing. Now the channel is called label, so we have labeling information. I also do some subsetting just to make things go fast. If you want to run the full analysis at home, you can do this as well. Just ignore this chunk. Now the next step, we have our 2 data, but they're still like simple tables. We use the QFeatures structure. So QFeatures is a software that allows you to streamline data manipulation in proteomics experiments. How does it look like? If you're familiar with a summarized experiment, well, a QFeatures object is a list or a collection of summarized experiments. Here it's 1, 2, 3, for instance. What is the main property of the QFeatures is that it allows to connect different rows of the summarized experiment together. And this allows us to record. So we start from this PSM data, and we're able to, if needed, we can build a peptide protein table while keeping information between the different runs. A paradigm in QFeatures is that we never transform the data, we duplicate data. So if we apply a processing step, instead of losing the previous step, we keep it and then we make a new copy. And so basically, the list of QFeatures, the list of a summarized experiment in the QFeatures object provides you with a list of the different processing steps that happened. In the summarized experiment, there is row data providing you annotations on the row. So for instance, here every row is a PSM, or every row would be a peptide, or a protein. And then we have annotations for the columns. Again, well, in this case, the properties that we have the columns in these assays should be the same as in these assays, So what is happening is we have a call data for the samples here. It's a common call data for the different samples. So we can retrieve these information quite easily. Let's see how that works. We will connect the two tables. So for instance, I showed you here. Oh wait, but we have some columns that are called that have the quantitative information, and we now want to link that to the sample annotations. And so what we have is in the column, of the quantitative data, of the annotation data, we have this information from here. We have the channel, so we can know from which channel within a run every sample belongs to, and we have different runs that is given by this run. So for QFeatures to work, what it needs that the sample annotation has information on the run column. This one is provided by the column run. It also needs to know, okay, what are the quantitative columns in my PSM data? And this is the sample labels that were used. And remember, in the table I just showed, these sample labels in the PSM data, they start by abundance and then the name of the label. So we add those two information to the sample annotation, and then we can use read QFeatures. Read QFeatures takes the PSM table, takes the annotation table. We need to provide him, okay, what are the quantitative columns so that they can match them. And then the run column that we provided here, where can you find it in the PSM table? It's in a column called spectrum file. I can show it here again. Yep. Spectrum file. So these are the different names of the runs. So now I can match the different runs, I can match the different channels. Yep. And we can run read QFeatures. You can see the different thing. It checks arguments. It's loading the data as a summary experiment because it was just a table before. It splits the data in different runs, because if you remember, there are different quantitative columns, but they correspond with different runs below each other. So one column is not a sample. We want one column, one sample. So we just chunk the table into bits. This is what this does. We have the sample annotations, and it makes a matching between, okay, the different samples, the different columns, the different samples. And then it puts everything together into a QFeatures. I change quickly the names. And then I print. This is a print of our object that we obtain. So we say QFeatures has different sets. We have 27. So remember, we had 3 mixtures, and every mixture has been split in 9 fractions. So we have in the end 27 runs, and every run is contained in the sets. You can see every run has 198 PSMs and 10 columns, 10 samples. But these numbers are quite low. This is because I did some subsetting before. Okay. Now, yeah, so we have this in a QFeatures. How can we retrieve these different pieces of information? Well, we can just get them here. Oh, yeah, wait. But this is a bit tedious output. Well, so this is our call data. We just imagine we did the call data, the 6 first rows of the call data, and we have here our annotation table that has been matched with the rest of the data in our QFeatures objects. We also have PSM annotations. This you can retrieve with the row data function. If I show you there, we retrieve all this extra information that the search engine provided. And then finally, what is very interesting to us is the quantitative data. We can retrieve it thanks to the assay function. So yeah, something I didn't say for the row data. So you have a row data for every set. We have 27 sets. So what I first do is, since QFeatures is you can see this as a collection, we can subset for the first set. And so this is the row data. This was the row data for the first set. We can also retrieve the quantitative data for the first set. Again, subsetting for the first one, but then using the assay function, which retrieves the quantitative data. We can see here the different quantitative values that were retrieved. Now, final step before getting to the data pre-processing is some search engine encode missing values by a 0. In mass spectrometry data, a 0 has a very specific meaning. For instance, I mean, in RNA-seq data as well, I mean, a 0 count has a very specific meaning. But in proteomics, since it's an intensity-based assay, a 0 really means like I measured nothing. But you cannot distinguish something. Well, you cannot say it's a 0 because that one feature I was measuring is just 0, indeed 0. I measured the 0. Or is it 0 because just it's not there and I couldn't measure anything? So we prefer to put every 0 as encode any 0 as a missing value. This will be for the modeling part, which will be much more explicit and will avoid artifacts. So that's always good practice with mass spectrometry-based proteomics. Any 0, replace them with a missing value explicitly. Okay, so that's it for the data reading. Do you have any questions maybe at this point? No? Okay, great. So then we can move to the data processing. We have read the data, but the data is not ready for modeling. We need to make sure that it complies to the assumptions of our model. The first thing is we need to remove PSMs, so features for which we have a low reliance or that contain no meaningful information. And the first thing is, let's remove features for which there are too many missing values. And so to remove missing values, we use QFeatures as a function called filter NA. Filter N. Mouse is the name of our QFeatures object, and we say filter NA on all the names, all the elements of mouse. And what we want to do is we want to allow for maximum 70% of missing values. So we apply this filter, and so well, I mean, do we have the previous output? Well, I mean, in the end, we still have QFeatures, and if you have very good memory, I don't, but you will see that some of the rows got dropped because they have too many missing values. Next step is we want to remove failed inference. So peptides need to be mapped to a protein, and sometimes that process is either did not work, so there is no protein accession, or sometimes, well, I said one peptide can map to multiple proteins. This brings a lot of ambiguity, and in this workflow, we decide to remove it. So we want to remove protein accessions that are empty, or protein accessions that contain multiple ones, which is basically protein accessions that contain a dot column. Yeah. I mean, so this one, sure, because actually if you come up with something that's differential detect, super interesting, and you cannot map it to the protein. Again, maybe depending on the use case, but yeah, the researcher will get frustrated saying, yeah, but I want to know what did change, what is the protein that changed. This one, you can still say, no, I don't care. I'm happy to see like groups of protein together, or like a peptide changing, but without being sure of which group it changed. This often occurs with isoforms, so which there is a high sequence similarity. Yeah, sorry. Yeah. Yeah, this is actually a good point. This is something, well, there is no direct function that we provide to do that. I will show afterwards. You can also customize your filters. And so here I didn't demonstrate how you can customize the filter in that specific context, but you could implement, I mean, you could provide some measures to do it yourself indeed. Yeah, that's possible. Yeah, sorry. Yeah, I mean, yeah, in fact, in this workflow, we recommend it. Yeah.
Okay.
Yeah.
Like the summarization step, the function will take into consideration that there is unique, but also the same, have the same implied shared if I give.
So again, there is, and I don't show it here, but there is a function in msqrob2 that will allow you to kind of simplify this, because it's true you can have some peptides that map to one protein and then other peptides that map to a group of proteins, but these group of proteins, or that first protein can be contained in groups of proteins. There is a function in msqrob2 that allows you to simplify these issues. Yeah, indeed, that's possible. Again, I didn't demonstrate it, but yeah, good question. So we want to filter on these protein accessions, and so this information protein accession is available in the raw data, so in the annotations of sense. And we can access these information through the filter features object. And basically what filter features will do is it will apply this condition on the raw data. And as soon as it's true, it will keep that feature. If applying this filter returns false, it will remove it. So in this case, we don't want it empty, and we don't want it to match .com. So we don't want it to be a protein group. So now I was mentioning this customized pipeline. There is, in the study, it was suggested, there was an additional issue. It's like for one peptide ion, well, you may actually have multiple PSMs. And well, this brings some ambiguity. If you want to start analyzing the data at the ion level, well, how do you manage these different PSMs? What the authors suggest in the analysis was actually to keep the PSM with the highest intensity. I mean, this is some criterion. I mean, I'm personally not convinced by this. So we got inspired by the authors. But this would require more benchmarking to understand, okay, how should we deal with these ambiguous PSMs that map to the same peptide ion? Anyway, I think this is a very good example for how, so this is not standard, this is not proposed in QFeatures. This is a good example for, suppose you have your own variable that you would like to implement. How can you do that? So what we will do here is we will make a new variable in the raw data. We will call that variable ion ID. The ion ID is defined by the peptide sequence and the peptide charge that was measured during the experiment. We compute the row sum. So for every spectra, we see, okay, what's the intensity of my different labels for that specific spectra? And then we will rank these intensities for every peptide ion in each run. Then we store the information back into the raw data, meaning that we can then use filter features to run it. So that was the kind of text form. How does that look like in a code? We will basically look for every set. We compute, we get our raw data, and then we compute our ion ID, which is the annotated sequence and the charge. Then we compute row sums. So we retrieve our quantitative assay for that set, compute the row sums, and then we have our raw data. We take our raw data. This is by the way, dplyr functionality. We group for every ion ID. We just want, so we want to rank within each ion ID. We rank based on the row sums. We call this new rank the PSM rank, and then we inject that raw data back into the row. We inject that modified table, that modified information containing the PSM rank back into the raw data. What we want next to do is to use the PSM rank. We want only the PSMs with the highest rank. Note that if there is only one PSM per peptide, well, the rank will always be 1 for them. We want so the PSM rank we want, and we use this for the filter features. So let's run this. So again, here the code is a bit more complex, I agree, but this really shows you can, once you understand this, you can basically implement any filtering criterion that you would like. Yeah.
Is there a reason you have done it like that and not wrote an aggregation function that just keeps one PSM?
I mean, that would be another example. We could have an aggregation function. Yeah, I mean, to be honest, yeah, that would be an alternative way, indeed. Anyway, you will still have to go through that loop to have this rank information, and then instead of having a built fish, you could have an aggregation function. But I mean, that's possible. So now, up to now, we had PSM data, but basically we removed, we made sure that every peptide ion is quantified by a single PSM. So we actually now have peptide ion information. And I will refer to it now as peptide ion data. Okay, now we have, let's say, reliable data. We discarded all the rows that were not of interest for us. We can now start doing the actual pre-processing. Pre-processing consists of 3 steps. Here in this, I mean, we suggest to implement at least these 3 steps. First, log transformation. It's important to know the proteomics data, its intensity, but there is a mean variance relationship. What does that mean is like lower values are expected to have a smaller variation than when you measure high values. To cope with that, we use log transformation. There is also, yeah, I mean, I won't go into, if you're interested into more details, I've put more text. There is also normalization. There might be during the experiment some little shifts when preparing the samples, but we want the distribution of the density of different samples for which we expect to be similar. We want them to be well aligned. This is the step, this is the purpose of the normalization step. What we will do here is we will align all the medians together. And then as an optional step, we also have aggregation. We just mentioned this before. We're working now for the moment at the peptide ion data, but you can also say, I want to aggregate I want to combine my data, my different peptide ions into its original protein. And so we can have a protein aggregation step.
Something that is important to do that is that you have multiple ions from the same protein. And then it's important that you do that with a kind of a linear model that is estimating both the sampling effect, the summary, and corrects for peptide. And if you do that, you basically acknowledge that different peptides are different to the master. And that will give you more options. That can be really easy.
Yeah. So again, as a code, this is how it translates. So we have the log transform function. We use a base 2 log transformation. We have the normalization. What we center the medians. And then we have the aggregation feature. And here we use the median polish. So this, indeed, as Lieven said, is so this is the aggregation function that takes into account that different peptides can have different densities. Well, again, in this case, this has been used by the authors. We also would suggest, well, in an LFQ settings, we would definitely suggest for rubber summarization. So here in this case, this summarization is performed for every set separately. So we subtract the medians for every row and the medians for every column in a separate run. So we account for the spectrum, well, partly account for the spectrum effects. That every spectrum can have different baseline information. But in an LFQ, it's also, yeah.
Actually, the two approaches fit the same model. They both model sample effect and by correcting for peptide effect. Median polish is using median sweeps, those medians of rows and sums, rows and columns, and that's a robust way to do that. And robust regression is using the robust regression is slower. So if you have lots of data, median polish is fast, but the robust regression is a little bit more like compete against.
So okay, that's it for the pre-processing. A very last step is in the condition. There was this different diets. Then there are two conditions which are actually, well, this is a normalization channel which we didn't use. We decided to use another normalization first. There is this other condition which, to be honest, is not documented in the study, so I don't know what it is. We just remove it. We can remove it using the subset by call data. We don't want the norm sample, the normalization samples, and we don't want these undocumented samples. All right. So now how does maybe. Sorry. Yeah. It's not. So what does our data look like now? For every step we added new assays, and let me zoom here in just a few of them. So here we had all different runs, and you can see, well, it's like this. From the name, what we did is we first log transform. You see there's a little log on it. Then we did normalization, and then we did aggregation. So now we have different routines. But you can see they're all now, like all these data are contained in different sets. And for modeling, it is you have to get all these data into a single set. So we use the join assay function. We will join these assays, so the normalized data, so the normalized peptide ion data. We'll normalize it based on the ion ID. So that's the ID of the peptide ion. This is for the peptide ion level data. And then for the protein data, we will do the same thing. This time, well, every row is a protein, it's annotated by the row name of every set is a protein, so we don't have to mention how to join it. It will join it automatically based on the row names. And then we can see here that our two last sets are now the ion normalized peptide ions and then the summarized protein assays. Okay, so that's it for the data pre-processing. Any further questions on this? I was actually planning to take a break, but since we lost a bit of time, is it this one? No. Here. Yeah, I don't know how to shut it down, but yeah, better. All right. So except for echo, is there any other questions? Yeah. Yeah. Yeah, actually, this is an excellent remark, and this is, to be honest, this would be my intuition of doing. Yeah, so something I should mention is like, so here I'm showing a workflow, but as you can see, every step is performed independently, so you're free to like switch steps. So but I agree with you, but the authors did it that way. I'm muted.
It's also.
Oh yeah. Okay. Happening. Wait. Yeah, I'm sorry. It will be without my face. I just can't. Okay. Yeah. Okay. So so now let's try to now we'll get into the data modeling. Okay, and for this, I would like to take the experimental design in the discussion. So you remember there are potential different sources of variation. First, we have our sources of interest. We know we have two diets, high fat and low fat, and we know these diets have been applied for either a short duration or a long duration. Then we have our different mites, our different biological replicates. They have been mixed together into 3 different mixtures, and each mixture has been split into 9 fractions. You can see, for instance, here the annotations for our factors of interest. Well, we basically have 45 samples. So remember, we have this is 5 mice per condition times 9 fractions, so 45 samples for every combination of factors. You can see this is a balanced design. So we have as many observational or as many samples for every condition. What we will now do is explore, okay, how much do these, some data exploration to understand, to get an intuition of how much do these sources of variation influence our data. So to do so, we will look at the protein data. We take our, so on the right, our QFeatures object, and we will extract the summarize experiment object. And we do this thanks to the get with call data function. This function is interesting because it will extract our summarize experiment of interest with, as it says, all the call data, all the sample annotations that comes with it. So we do this, and now we can see we have now summarized experiments with all data. And then we will use the package Skater. Maybe some of you are familiar because it's well used in the single cell literature. It provides a lot of different dimension reduction for and visualization functions. Since it comes from the single cell experiment field, well, we need to convert our summarized experiment in a single cell experiment class object. This is just a detail, you can simply ignore it. And what we will do, we will perform MDS, which is a dimension reduction methods that try to optimize to keep as much as possible the distances between the points in the high dimension, while to keep these distances as representative as possible in the low dimensions as well. We run the MDS. It is stored in the single cell experiment object, and then we will plot the MDS. We will plot it by. We will plot. It's exactly the same plot you will see multiple times, but we will color it with our different factors of interest. So run, fraction, biological replicates of mouse, mixture, diet, and so on. Oh, let me. So we see here. So these are six times in the same plot. what can we see? Let's first look at the MDS by run. We can see that every point here is a sample followed by run, and we can see that samples that belong to the same run tend to cluster together. This indicates that there is a strong run effect. Intensities from samples that belong to the same run will tend to have more similar intensities than samples from different runs. These different runs, they come from fractions, and we can actually see also that runs from the same fraction tend to cluster also together. So this run effect seems to be partly influenced by the fraction. Within each run, we have different mice. Here, it's difficult to see. Okay, there is like samples coming from the same mass together. So, which indicates that the run effect is more important than mouse effect. We can here not exclude. There is no. And then
the main thing that we have no fractions. So we have nine fractions for every mouse, so data.
And then for which similarly we seem to have a small, especially in the sample, we seem to have some clustering of mixtures, so mixtures seem to have also a slight effect. And then if we color by diet, if we look, for instance, this run, when we color by diet, we see that okay, some samples within the run seem to cluster by diet as well. And if we look at this clear, there's some effect. But the take-home message from here is we can see there is some strong sources of variation, namely coming from the run, and we need to take that into account if we want to understand what are the differences or factors of interest. What's this? And so this is why we need to define clearly what are our sources of variation. So as I said, the first source of variation is the freedom of interest. We have an effect of the type of diet and the effect of the duration. We'll model these effects as fixed effects. So what I mean by this is we will ask, well, since these effects are effects of interest, we will assume that if we repeat the experiment, we plan to find the same treatment of interest. Also, something we will do with this diet, we will also account for the fact that maybe the duration may influence the difference that we have between the type of diet. This is called an interaction. So we will allow the duration, the effect of duration to interact with the effect of diet. We next have our biological replicates. So the difference, so we have different mice, and we expect that intensity from one intensity of measured within one mouse will be more similar than measures across. There are many things that influence the mouse, and we cannot expect. I mean, every experiment will have different mice, and this is not something that we can reproduce. So if we have to do this experiment multiple times, well, every mouse is different, so we have different effects. We will therefore model these sources of variability. The source of variability belonging to mice will model it as a random. So yeah, so the random effect it puts an assumption. Yeah, it would put an assumption that it doesn't. Basically, what it does mean also, what it will assume is that the effect of mouse is distributed. It's normally distributed around 0 with some variant sigma associated. Sorry, I was hoping it will render, but oh wait, I know.
This data, what we basically have is that we can see that the effect of this like a hierarchical. And we will basically model this blockwise correlation stuff.
So we model the effect for what we define the effect for type of diet, duration. We also define an effect for mouse. Now we also have labeling. The fact that you put a label on the peptide may also have an. This is called the labeling effect, and we expect that peptides that have been labeled with the same label will be some more correlation or more similar than samples for which there are different labels. We also have 3 mixtures. Again, we expect that samples from within the same mixture will be more similar than samples from different mixtures. Okay, and so the labeling effect is, again, I mean, depending on the kit you're using, these labeling effects may be different. This due to impurities or things like that. Therefore, we will assume that these are random effects as well. So they are not reproducible, and the mixtures effects as well. We have then the run effects. So these 9 fractions. Well, when you send your material into the mass spec, there are many fluctuations that make that your acquisitions may be different, and we just saw that this can have a big impact on your measurement. So we will again include an effect for run, assuming that samples coming from the same run may be more similar than samples coming from different. And the effects of a run, I mean, from run to run, you cannot reproduce these effects. I mean, this depends on some conditions. So this will again be these are not reproducible. So we will also model them as a random effect. And then you also have a spectrum effect. So you have different samples that are labeled. What you expect is that the information that's contained in one spectrum will be more similar because it's subjected to the same fluctuations than data coming from different spectrum. Again, we will use a random effect to account for these spectrum effects. And then finally, because when we're working with peptide ion data, we want to model at the protein level. So this means that we have, for one protein, we have multiple information, we have multiple peptide ions that are for every channel. So the idea is we expect that sample that measure for the same label across, so for the same protein across the different spectra will be more similar than the intensities that you have for a for different label across the different spectra within each run. This is becoming complex. So maybe let me try to explain this again. So we have different runs. Yeah, or even if you want to clarify.
The way to see it is that you have a sample, you have a protein pool and a sample, and you just start testing the peptides, and you use all these peptides.
Okay. Yeah.
And I guess that's
what I mean.
That's exactly what you. Because we don't put anything that we use peptide we directly and therefore you can see this peptide intensities as technical reads of the protein value, and we will have to model that together and have to acknowledge that. And if you would model them right away without acknowledging that they are correlated, you would do as if every peptide is an independent measurement of the protein. You have reading, but so that's it.
Yeah. So yeah, only this is how we define a model. So we say we want to model the effect of light and duration. And we have this little associated model and interaction between these two, and then we use different random effects I just went through. Okay, we identified potential sources of variation. We defined our model. We can now estimate the model. And so to estimate the model, we will use the function msqrob aggregate. So that now we're getting into the core functionality of msqrob2. What msqrob2 is going to do, it will take your QFeatures object, and then you need to specify, okay, which one of the sets do you want to analyze? You need to provide, okay, what should I model? What are the effects that I should model? Those were specified in the formula here. Something very interesting with msqrob2 is that you can, starting from ion data, you can make inference, you can assess changes at the protein level. But you need to specify the function, okay, which ion belong to which proteins. And this you can do with by providing this argument saying protein accession. It will the data will be stored. So the output of our model needs to be stored somewhere. It will be stored in the raw data in a column called that we call msqrob2. And then also it will have to so since we have this peptide ion data, but it will collapse the statistical analysis into the protein level, we need to make a new set containing these estimated model at the protein level. And this new set, we call it proteins msqrob. And then finally, the other very interesting feature of msqrob is that you can perform rich regression. And rich regression means you can establish, so you will estimate the coefficients for your effects of interest. But this may sometimes be, well, you may have multiple parameters and you may have some sort of overfitting, while rich will allow you to stabilize the coefficients and avoid overfitting. And we use, well, there is a link between mixed models and rich regression to find the best regularization parameter. So you don't have to, well, for those that are used to rich regression, you don't have to specify penalization. And then finally, it is robust. So it won't be sensitive to outliers. That's also something, a very interesting property for mass proteomics. Okay, let's run the model. Yes, indeed. Great. This can take a little bit of time. It will go through every protein, start fitting the data. Would you have any questions on this point? Yeah. Yeah. So I will just show. Indeed, I didn't mention it, but I will provide two scenarios: aggregating at the peptide ion data, or you can also aggregate at the. Or you can also model at the protein level data.
That's something that we started to do. When sometimes we started to model the data, and see that it is having high ground. But what we have seen that it was rather difficult to disseminate to researchers, and that they often not have identity protein as expression values. And therefore we have two workflows, either starting at the peptide level, model peptide data right away and providing the peptide expression at the protein level from peptide level data, or summarizing first and doing it traditionally.
When you say that for this study, and what would you do normally? Just take the sum of the other. All the PSMs of all the features.
Yeah. So my, again, this is not something I benchmark, but my feeling would be, okay, if you have different PSMs for the same peptide ion, well, you don't really know which one is correct. I will just remove them all. But that would be my take. No. Or did I not understand your question?
In peptide sequences, different charge.
Okay, that's what you mean. How to aggregate them to peptide then?
Or sum it up.
Yeah.
Ion data from ion to protein, and then using them as because they try different people. Another option would be to summarize them first into peptide level information. But we have seen that it's often better to work from the lowest level and summarizing immediately. So that's something that has been reported. So if you first do peptide level, if you first have PSM level data, then aggregate to peptide level data, and then aggregate to protein level data, for the PMP, and the PMP has been acknowledged by several papers that going from PSM level data right away to protein level data is better than taking all the intermediates. I think that there I have not perfectly benchmarked it yet, but I think that's similar. What you basically have is, especially in TUT data, it's very important to keep the information of the spectrum because you have all the ions in the same spectrum. So having that together is useful. If you first would sum them up, you would maybe lose track of that. So therefore it's a good idea to go from CSM level data, right? That's one thing. For label 3 approaches, again, we often start from peptides, some peptides, and data as well. Where should I?
So it's going up.
So the entrance is at a protein there, but we start from peptide level. So we do differential abundance. We estimate fold changes at a protein level by modeling all the by modeling all the ion level data. Okay. Yeah,
Yes,
that's
exactly.
because we aggregate it at
Then this is why it's important in the protein. That is protein.
If you have a protein group that is empty, then you would consider all the peptides that have not been identified to come from the same
If I have like many different proteins, this is all
Yeah.
fake.
Yeah.
So
Yeah.
and this is why also I was asking about I will insert tags in this step, the peptide and protein is not connected.
Yeah,
So
but
if I just take the aggregate proteins here, I inserted the max the model work of the peptide.
But then I would not even bother about getting in the peptide data. If you want to work with the LFQ data right away, everyone goes, I would just go with the LFQ data right away.
And do just
Then I would not start to bother trying to link the data and stitches.
So now comes the fun part, like the part where we start answering biological questions, and this is known also as hypothesis testing. The first question we can ask is, okay, imagine I have for the short duration of a diet, what is the difference? What differences in protein abundances does low fat and high fat induces? To do so, we need to convert this English question into a mathematical combination of parameters that we just estimated in the model before. This is known as a contrast. This combination of parameters is known as a contrast. And this is probably the most, not the most important. This is a very important part and sometimes can be quite overwhelming, especially if you're not very much into the data modeling. But there are there's a very interesting tool called the xPro model matrix, which allow you to convert, to simplify the conversion of these model parameters into the contrast. So here the question is, so for a short duration, I want to know what is the difference. Oh, sorry, I should explain what this graph is showing. This graph is showing 4 boxes. 4 boxes that are actually the 4 conditions. And what is inside the 4 boxes, it's the combinations of parameters that provide me what is the average intensity in that condition. For instance, if my duration for the long duration and the high fat, the average protein abundance is modeled by the value of this. On the other way, if I want to have high fat at short duration, it's the average protein abundance is given by the intercept plus the parameter called duration short. In our case, we're interested into at the short duration. What is the difference between low fat and high fat? So what we do is we have this average protein abundance given by these sets of parameters, and we subtract it by these other combinations of parameters. If you look, if I subtract intercept and intercept, this cancels out, and duration short and duration short, they cancels out. So what remains is basically our differences between 2 is diet LF and diet LF. This is the this is our contrast telling us the differences between these two conditions.
And because we model on the log scale, you directly have the main effect.
So this is what I provide here. My contrast is the combination of these two parameters I just found. Okay, next is, okay, this is a contrast, and I want also a hypothesis. What is my null hypothesis? When we do hypothesis testing, we also always have to define a null hypothesis. And here I'm interested in, is this differences between these two groups different or not than 0? So my null hypothesis is that these two parameters, the difference is equal to 0. So now we have defined how to combine this contrast. Well, we need to build what is called a contrast matrix. Is basically like, you could see this as a mathematical sentence to explain what we want to compare. So the mathematical translation of our biological question. It just takes our hypothesis and the parameter names that all fit in the model. And we can see, for instance, okay, so for this contrast, well, we need the parameters called rich. Well, this parameter, this first parameters plus this second parameter given by the coefficient here, and in this case, yeah, that factor that parameter name, we didn't need it. Now we have our contrast, which I called L. We can do the hypothesis testing. So hypothesis test, what it will do, it will take my QFeatures object. I stored the model estimation inside the set called proteins msqrob2. This is my contrast matrix, and yeah, those models were stored in the raw data in the column called msqrob2ion. So I can run this. It's very fast, and then I can retrieve my results inside the raw data. So I have this msqrob set. Oh, sorry, yeah, I'll show the raw data. So what I didn't show it previously, but these are, for instance, all the model estimations that we stored previously, and using these model estimation hypothesis, the function hypothesis test created a new column containing a table, and this table contains all the statistical inference. Let's extract them from there. Yep. And this is how it looks like. So we have a log4 change. So what is the estimated differences between our two groups of interest? The associated standard deviation and degrees of freedom, which are then used to compute a p-value, which we adjust for multiple testing using Benjamini-Hochberg testing correction. And then here I also added the label of the, okay, for which protein does that come. You can see that there are some rows with NAs. And you saw also, like, when I run the estimation, there was some output giving up. Well, sometimes because of patterns of missing values, or basically because there is not enough data. Some proteins could not be fit. So that's, yeah. We provide a vignette. In another vignette, we provide solutions for how can you accommodate for these fat errors, but this is like, we won't have the time today. So obviously from this table, the first thing we can do is plot this as a volcano plot. And this is how it looks like. So for our short duration, the differences between low fat and high fat are given by the hypothesis testing leads to this volcano plot. You see some proteins are more more important in the low fat, and other proteins are becoming more abundant in the low fat. We can now say, okay, this is interesting. This provides me an overview, but I would like to know more, to dig more into the data. So because we store always the data, we can go and see, okay, let's check what the model saw, and do I intuitively trust it. So we will, here in this case, we will extract the protein with the highest log4 change. I mean, this is just an arbitrary, you could use any protein you want. to explore. And then we use a little QFeature data manipulation pipeline to explore the data. So what we do here is we take our QFeatures object, and we can, I didn't mention this in the beginning, but something interesting is we can also subset all the data for one specific protein. Here in this case, we'll extract all the information for our target protein. Here, I mean, we could plot all the data, but to make the plot a little bit concise, I will just focus on the data that the model has seen, so the normalized peptide ion data. This will do some subsetting, providing a QFeatures. This QFeatures object cannot be plotted using ggplot. So what we will do is we will make it a long table, basically. Put it in a table format that can be read by ggplot. This is thanks to the long form, and we will include not only the quantitative values, but also the call data information and some raw data information. So we will include here all the call data information in our table and these raw data information. We remove missing values, and we will focus, because we looked at the shorter duration, we will focus only on these data. And then the last step, you can basically ignore it. It's to make the sample better ordered. So our ion data, how does this look like? Well, we have our assay name, our column names, the row names. There's a column names again. The quantitative values and the different sample annotations. And this all sample annotations and the row annotation. So with this format, we can simply plug it into ggplot. And then what I want to see is I want to plot I will just show it. So in this case, what I show you here is every point here is a measurement. I have passed it for the different mixtures. Remember, we had 3 mixtures. So I did that to see, while there's some noticeable mixture effect, it doesn't seem to be on the intensity values, but we can see there is some difference. There is more missing values in some mixtures than in others. And then I have these 2 conditions, either high fat or low fat. I colored each point depending on the low fat. And then so these are all the data belonging to one protein of interest with a large log-fold change. But each of these proteins, or this protein, was measured through multiple peptide ions, and I connect all the peptide ions with a line. So this allows us to understand, okay, what did the model see? And you can see that all the lines, they tend to shift, to be consistently shifting upwards. And so indeed, this is expected, but indeed the model showed us a log-fold change, and I see here this makes sense. So now we can ask another question. They say we focus on the short duration. We can now do the same thing, but on the long duration. I'll again define my hypothesis test. I mean, going exactly through the same process I explained before, subtracting the parameters from the 2 groups. Well, for the long duration, it leads to this combination of parameters. So this is my null hypothesis. I build the contrast, and I just go through the exact same pipeline I just went through for the first question. So the only thing that changed here is the hypothesis test I defined. So here I'm basically going through the same steps, but asking another question. And because I asked another question, I got other results. So we see that if we change the duration, the effect, well, there are much less proteins. So something we could say is like, maybe in this long duration, there was something with the data. Maybe I want to see what's the average effect. I don't want to care anymore about the effect of duration. I just want to look at the average difference between low fat and high fat. So we do this here. Again, trust me, this is the combination of parameters if you want to compute the combination.
So it's basically the first part is a fold change in the long duration plus a fold change in the short duration, divided by 2, and if you then see that this is equal to the main effect plus the main effect plus the main effect with the interaction divided by half. Which is the effect.
Yeah. And so again, I just changed the question, so I just can use simply the same workflow, and because I asked another question, I got other results, and this is the results we get. And yeah, I mean, you'll see it afterwards, but the idea is well, we'll see it afterwards. But these results kind of combine the two previous results. Yeah, meaning that like we used here in this case, the fact that we average over these two short and long duration conditions, well, it allows us to get more data. But then another question we could ask is say, all right, so we saw that there are differences between long and short duration. Another hypothesis could be, oh, actually duration has an impact on my differences. So let's ask this as well. So does the fact of having longer or shorter duration, does that impact the effect of low and high fat diet? So this is
so it's actually instead of twofold change between low and high fat, different if you compare the long and short duration. That's what the interaction is. The difference in the
exactly. Well, again, just same story. And then here what we see is that like the effects, they barely, well, there's one significant protein we find out of this. So for most proteins, we can say that duration there's no impact of duration on the differences between high fat and low fat. But there's this one protein, it would be interesting to see, it's interesting to see, okay, what is that protein? What did the model see? I used the same pipeline as I just showed you before, and I built kind of the same plot. So remember before I was faceting for every mixture, so now I followed the same faceting now in this direction. And I faceted also the long and short duration. Well, I mean, we can kind of guess here, it seems that there is no effect. Well, first of all, here we can see this mixture. Well, there's probably, we don't have data from one of our conditions, so it will only relies on two mixtures. Here you can see that there's a few data points, here there's many data points. And whereas here we don't see an effect, here there's a slight effect. So yeah, it's borderline significant, and we can now ask ourselves, yeah, is this because imbalances in the data or not? So we identify this protein, but I would recommend doing some experimental validation to make sure that this is indeed correct. So again, I think, well, my opinion is it's quite important to look back into the data, making sure that our significant proteins are they really reliable. And I think in this case, I wouldn't rely too much on this finding. So yeah, I answered every question separately through different hypotheses, but actually with make contrast, we can just provide multiple hypotheses together. And then, yeah, I mean, so the only thing that changed here is this set of hypotheses. We can build a contrast matrix. This time it contains multiple contrasts. In the previous print that I showed, there was only one column. Here now we have multiple. I mean, again, this is maybe just a detail, and then we can run our hypothesis tests and extract all different inference tables now. So before it was just a simple table. Now we have a list of table. And with our list of table, we can loop through our list of table and make a volcano plot. Patch them. It just, well, I mean, this may be no clear, but it's basically exactly the same code I used as before, just here looping over the different tables. And then we get the volcano plots. Oh, no. Then we combine, sorry. So we have a list of volcano plots, and now I just wrap them together. And I get all the volcano plots in one go. think that is also interesting to, and we have all the different hypotheses we tested and the questions we asked. Now we can more easily compare the different the results to the different questions that we asked. Actually, for sake of time, I won't show the results on the protein level, but the idea, just to tell you what changes, because now we're working on a protein level data, we don't have these spectrum effects that we had before. Also now, within every fraction, for every fraction within every run, well, we just have one measure, so we cannot start to measure the sample effects. So there are two random effects that are dropped, but otherwise the rest is just exactly the same thing. Instead of msqrob aggregate, we don't need to aggregate anymore. We're working on protein data, so every protein, so one, let's say, line in your assay will provide one model. So we don't need to, well, it's not a msqrob aggregated, it's aggregated at the modeling level. So here the model is just one model, one protein, and one line, one model, sorry. And then we do this hypothesis testing. It's exactly the same thing. We get the volcano plots, and we and if I to run everything, well, I can run everything. Yeah, the key idea is basically we get more or less the same results. There are some differences, but as Lieven said, as on an answer on the question, we found that for TMT, the peptide on a spike-in dataset, so with ground truth data, we found that modeling the data on a peptide ion level is provide more sensitivity than at the protein level. Probably because we better, the design is quite complex, and we explicitly model for this complexity in the data. All right, yeah, maybe waiting that it's finished. Yeah. Okay, yeah, please trust me. Getting tired. So yeah, just maybe a wrap up, and then I let you go. So I was just wanted to say everything has to do with pre-processing. It's the QFeatures package. There are different steps: normalization, filtering, transformation, summarization, and actually more. You can also do stuff with interpretation with different methods. I showed you one workflow, which is a workflow that in our hands work well. Maybe you have better ideas and you could improve on this workflow. And I think this is very fruitful to have this possibility to incrementally improve our workflow. So we want this to be very customizable. We modeled various sources of variation. So there was all effects of interest, diet, duration, but also strong run effects. There was the effects of mixture. We also modeled the effects of labels, spectrum, and sample. Yeah, well, I didn't go into too much details, but we modeled the data at the ion level, but you have the choice. You can also model it at the protein level if you prefer. Yeah, so something that is also quite specific to msqrob2 is that we rely, well, in the back as a backend, we rely on the Almer package functionality, and which allows for a very flexible experimental model specification. So here I illustrated how you can include interactions with factors, but you can also have numerical variables. You can, if you want, you can include splines. I mean, if you fancy that. The design I just showed you today maybe was a bit overwhelming. I think it's interesting to see like the complexer data set can be. It can even get more complex if we think about single cell proteomics data. Here we also have to take into account that every cell comes from a subject. So cells coming from the same subject are expected to be more similar than samples coming from different subjects. But you can also have much simpler models. For instance, with LFQ, while there are many, so like you don't have a label, you don't have a mixture because you don't mix samples together. You actually can't include a run because if you have no label, well, basically one sample is one run, so the run effects cannot be models. So the model becomes much simpler, but be aware that because we do not model the run effect anymore, well, this can in the end get into the residual, so basically meaning it will increase noise and decrease statistical power. So yeah, thank you very much for your attendance today on the workshop. If you want to run it at home, I have here a link. You can, well, if you want to cite the workshop, I make an archive on Zenodo. Sorry, and if you want to get in touch, is my email.
If you want to have the additional coordination free data, we have vignettes on the msqrob2 website, biocontact website, that are the simulated work where you just do the solution.
Exactly. Yeah. Thank you very much.